Computer science, primarily male-dominated field, despite the shortage of women, it still manages to pull large numbers of aspiring prospects. So, how is computer science as a field? Well, considering the number of people vying for jobs that fit within the current scope of computing, it can be justly argued that there will soon be too many in the computer science field. But the fact of the matter is that for the past few decades, computing has increasingly become a part of everything that we do, and the current scope of computing is immensely limited relative to the virtually limitless areas to which computing can be beneficial. While there are many people choosing computer science as their career path, there still remains a large demand and need of talented individuals versed in this field. This is why we're beginning to see, and will continue to see, a proliferation of computer science majors who will continue to broaden the scope of computing. These are the many untapped markets begging for computing disruption at the hands of the currently unfilled pool of computer science talent. My name is Caden Veos, and today we will be discussing computer science along with some subject areas relating to it. Programming, networking, and physics. You may or may not know how these relate to computer science, but either way, introductions are still a formality. First off is programming. Computers are capable of amazing things, from basic laptops which are capable of many things from simple word processing and spreadsheet functions, to incredibly complex supercomputers completing millions of financial transactions a day and controlling the infrastructure that makes modern life possible. However, no computer can do anything until a programmer tells it what to do. Programming is really one small topic covered in computer science. It's also one of the least emphasized in many colleges. At its most basic, programming is little more than a set of instructions that facilitate specific actions. Based on the requirements or purposes of these instructions, computer programming can be as simple as adding two numbers to something as complex as reading data from temperature sensors to adjust a thermostat, sorting data to complete intricate scheduling or critical reports, or taking players through multi-layered worlds and challenges in games. On a smaller scale, there is mobile app development, which is a set of processes and procedures involved in writing software for small mobile devices. Similar to web application development, mobile application development has its roots in more traditional software development. One critical difference, however, is that mobile apps are usually written specifically to take advantage of the unique features a particular mobile device offers. For instance, a gaming app might be written to take advantage of the iPhone's accelerometer, or a mobile health app might be written to take advantage of a smartwatch's temperature sensor. In the early days of mobile apps, the only way to ensure an app had optimum performance on any given device was to develop the app natively for a particular device. This meant that at a very low level, new code had to be written specifically for each particular device's processor. A majority of mobile application development efforts focus on building apps that are device agnostic. Today, Android is arguably the world's most popular platform for mobile devices. Android brings Google and the internet to users of smartphones, tablets, and other mobile devices. In the process, it's changing how we communicate with one another. Android app development is the process by which applications are created for devices running the Android operating system. Google states that Android apps can be written using Kotlin, Java, and C++ languages using the Android Software Development Kit, but using other languages is also possible. Android is all around us, in our homes, in offices, in cameras and watches, even in cars and TVs. For application developers, Android is an open platform that provides exciting opportunities for developing virtually any app imaginable, with a user base that continues growing every day. What is computer networking? To simply put it, computer networking is a study of how computers can be linked to share data. The concept of connecting computers can date back to the 1960s, when the Department of Defense led the first attempt to create a computer network that painstakingly linked a handful of computers around the US. We've come a long way since those times. Wireless networking has taken off, and networking is now considered an essential part of computing. A computer without a network arguably has little use in daily life. Computer networking involves many things coming together, and there are many challenges and important problems to solve in the field of networking. Some of these problems can include scaling hardware and software to very high speeds, effective interaction with user, privacy protection and security, seamless connection to mobile devices, and studying computer networks. Of course, a solid math background is valuable, as with the other subjects. In addition to calculus, important tools in computer networking and communications include linear algebra, probability and statistics, differential equations, and numerical analysis. Good programming skills are also very important. Although a good programming background may not be necessary for some of the topics under networking, networking protocols and software require a solid programming background. Since it became as essential as computing, networking solutions are actively sought by the industry, government, and military. There are many core networking companies that generate solutions purely in computer networking. However, any IT or software company today needs experts in networking. Typically, an IT company has a communications and networking division as one of its biggest divisions. The Spanning Tree Protocol, or STP, is a network protocol that builds a loop-free logical topology for Ethernet networks. The basic function of STP is to prevent bridge loops and the broadcast radiation that results from them. Spanning Tree also allows a network design to include backup links, providing fault tolerance if an active link fails. As the name suggests, STP creates a spanning tree that characterizes the relationship of nodes within a network of connected layer 2 bridges and disables those links that are not part of the spanning tree, leaving a single active path between any two network nodes. STP is based on an algorithm that was invented by Radia Perlman while she was working for Digital Equipment Corporation. Lastly, physics. Physics has many important impacts on computer science. This can include the physics of spinning disks. The amount of data that can be stored and retrieved from spinning disk drives are governed by the speed at which they spin. The limit of that speed is obviously a material problem, but the physics of the spin and the direct impact of that spin speed on data storage and latency is critical to modern computer science. Most personal computer disk drives of a given generation are roughly similar in this regard, but in the business world, there are important choices to be made between disks that spin at 7,200 RPM or 10,000 RPM, or higher. A disk spinning at 7,200 RPM is not likely to be able to sustain more than a little over 100 actions a second. This value could easily be doubled on a disk spinning at 15,000 RPM. Now, the slower spinning disks can be larger, but if you can't get data on or off that larger disk fast or at scale, you have to buy a ton more of them to architect a solution that will perform as well or better. That could mean lots of extra costs in space, power, or wasted capacity. The speed of light is directly relevant to computer science in lots of ways. It seems like a gigantic speed, but given the millions of calculations going on in a CPU or GPU, fractions of a microsecond matter. In long-distance telecommunications, the speed of light is directly relevant again. All fiber optics operate by sending light pulses. Every single light pulse is a bit of data. Lasers can create very discrete pulses and send them out, but the raw physics of the speed of light in a glass fiber dictates how long it will take to get that bit down the glass. Another thing you might want to look at is rate of heat generation in a semiconductor and its effect on its conductivity. This is also the reason why you need a huge heatsink for your tiny CPU. Apart from thermal dangers, static electricity also poses a threat to computers. What is static electricity? Static electricity is caused by a process called triboelectrification. Everything around us, and including us, is made of atoms, and every atom has positively charged protons and neutrons of which have no electrical charge within their nucleus or nuclei. Surrounding the atom are negatively charged electrons. The protons and neutrons in an atom do not charge, but the electrons can move from one atom to another. When two objects touch, they exchange electrons, which causes one object to become electrically positive and the other to become electrically negative. When an object touches another object with either an opposite or neutral charge, electrons flow. So static electricity is created when electrons move back and forth between atoms. The inner workings of our computers are extremely vulnerable to static electricity. The simple act of touching any circuitry or plugging in a peripheral while you have stored voltage dangling from your fingertips can be fatal to your computer. It is even possible to damage your computer with static electricity that you can't even feel because it is at such a low voltage. The damage to your computer from an electrostatic discharge can range from a simple plug-and-play device not working anymore to completely shorting out your entire computer. A static shock can be instant, or it can take days to weeks to actually settle in and cause any noticeable damage. If you're still wondering how these subjects can correlate with each other, picture this scenario. Let's say you want to make a three-dimensional multiplayer game. This would require you to utilize knowledge of physics to correctly implement realistic physical actions and reactions within the game. You'd also need networking to implement the multiplayer aspect, and programming to create the game itself and tie it all together.